Hey friends, what we're going to look at in this video is we're going to do a nice little review of domain and range, and we're going to look at the two different ways that we are able to write domain and range. So these two things are called set builder and interval notation. What you'll see is they both have their benefits, and what I need you to be able to do is to recognize both of them and how to work with both of them. Okay, you'll definitely have a method that you prefer. They're both correct. It just gets really important when you're reading maybe certain types of questions that you're able to recognize both types. Okay, so let's just look at a few graphs here as we go through. So just a reminder that domain, we're talking about our input values. So our domain is the input values of our graph, and it's the acceptable input values of our graph. It's where our graph exists for those, usually our x values. Our range is our output values. And so again, normally that's y, but in a contextual question, it could be height or speed or something, but usually for us, we write it as our y values. So it's the output of where our graph can exist. So let's look at a few of these examples. So first couple here that you can see, I've given the functions. These are linear graphs. Now, one of the things when you see a graph like this here or in your textbook, when the graph goes to the edge of the page, it's assumed that the graph is continuing. If you're drawing this by hand, what I would really like you to do is to draw arrows though, okay? And then that makes it 100% clear that that graph is continuing, okay? But again, if you draw the graph to the edge of the page, it is assumed that the graph is continuing on. So for the one on the left here, f at x is equal to x plus 4. I want to write the domain and range for this. So what I say to myself when I'm doing domain and range is this. I say, okay, does the graph stop going to the left? Does the graph stop going to the right? And what I mean by that is, what happens as the graph goes to negative infinity and as it goes to positive infinity? So does the graph stop going to the left? Does the graph stop going to the right? So what I see here is this graph continues going to the left forever, right? It's going that way forever. And so the x values can go to negative infinity, and it keeps going to the right forever. So the x values keep going to positive infinity. So what I'm going to write here then is the fact that our input can be anything, that the x values can be anything. So how we write that the x values can be anything is this. We say that x little e r. Okay, what does this mean? Okay, well, x, because that's our input values. Little e here means element of. And then this funny looking r is called a whiteboard R or a chalkboard R. Okay, but what that capital R stands for is the real numbers. Now, what we're making here is a little sentence, and this isn't a good enough sentence. This is something I would maybe text somebody, but it's not something I would put in an essay. So I need to tighten this up. I need to make a full math sentence. Here's your full math sentence. It looks like this. So what I just added in here, these braces they're called, means the set of numbers, x, and the vertical line means such that. So we've made ourselves a math sentence. The set of numbers x such that x is an element of the reals. Okay, that's a really fancy way to say x can be anything. Our input could be anything. Okay, so we need to be writing these things in proper full notation. That is a big deal. Now, what about my range? Well, my range, I say to myself, does my graph ever stop going down? Does my graph ever stop going up? What I'm really talking about here is, does the graph stop going down to negative infinity, and does the graph stop going up to positive infinity? And the answer is no. I can see that. It goes on in both directions forever. So my range is very similar. What I'm going to say is, again, that is y can be anything. That's y is an element of the reals. But what I want you to write is the proper notation, a full sentence. The set of numbers y such that y is an element of the reals. Now, this is called our set builder notation, which is a little more common when you're looking at some of the print resources. But there's a second way to write these. And how we're going to write these is called interval notation. So interval notation uses these parentheses. I'm going to write it off to the right here. And these brackets, okay? What these parentheses mean here, it means it does not include the endpoint. Not include. And I'll show you what I mean. And the square one means it includes. So in this case, this graph domain goes to negative infinity and positive infinity. So negative infinity, positive infinity, and because negative infinity and positive infinity aren't a number that I can put my finger on the number line, they're not real numbers, I'm going to put a parenthesis around it. And the same thing for the range. So you can see why some people prefer interval notation because it's really quick to write. Okay, let's look at another one, the one beside it. So it's another linear function. And again, I say to myself the same questions. Does the graph stop going to the left? So no, it keeps going on forever. And does the graph stop going to the right? No, it goes on forever. So the x values can go to negative infinity and to positive infinity. So again, that would be x is an element of the reals. So the same as the first graph. And I then do the range. Does the graph stop going down? Does it stop going up? No, it doesn't. So it's the same thing. Y can go to negative infinity and y can go to positive infinity. So our answers here are the same as the other graph. This is our most basic example. Let's try a few more. Now take a look at these two. When I start asking myself my little questions of, does my graph stop going to the left? Does my graph stop going to the right? Well, what we can see on this one is this graph certainly stops going to the left. It stops at an x value of -2. So does the graph beside it. But you see the open dot. So there's a difference here. The solid dot or closed dot on the first graph means it includes that point. And all of my x values are greater than or equal to -2. So how I write that is the set of numbers x such that x is greater than or equal to 2. X is an element of the reals. My range. Does my graph stop going down? No. Does it stop going up? Yes. At that closed point, it stops at +3. So all of my y values for this function are less than or equal to 3. Y is an element of the reals. If I want to write that in interval notation, all of my x values are greater than or equal to, so it includes +2. So I use a bracket and it goes to infinity. So comma infinity, parenthesis, because infinity is not a number I can put my finger on the number line. It goes on forever. It grows without bound, if you want to say that. Our range, all of the y values, the outputs are less than 3. So I go from small to big, -infinity to 3. So notice whenever we're writing range, when we start domain and range, when we start having values, we always go from small to big. Okay, so I like to again say from left to right, from bottom to top. Okay, and then we always write it in our notation the same way. Okay, the next one, almost the same, but now we've got that open dot, which means we don't include 2. So the subtle difference here is we're going to say x is greater than 2, but it doesn't include 2, even though it gets as close to 2 as it possibly can be. And the range doesn't include 3, even though it gets as incredibly close as it could be. How does that affect our interval notation? Well, if it doesn't include 2, I'm going to use a parenthesis like that. And if it doesn't include 3, I'm going to have a parenthesis. So when it doesn't include something, it's a parenthesis. When it does include something, it's a square bracket. Okay, so there's an example of two types of graphs where the graph ends going one direction. All right, let's try a couple more. On the next two, now our graph stops going in both directions. Okay, sometimes we struggle writing these ones. It takes a little bit of practice, but again, all I'm going to say to myself is, does my graph stop going to the left? Yes, it stops at -2, 3. And does it stop going to the right? Yeah, it stops at 3, -2. So my domain, what that means is my x values are between -2 and 3, including -2 and 3. So we write it this way, and always this way. Small to big, -2. What that says right there is x is greater than or equal to -2, but x is less than or equal to 3. Small to big, comma, x is an element of the reals. Range. Our range will be the same idea, small to big. So we stop going down at -2, and our y values are greater than or equal to -2, and they stop going up at y value of 3. Y is an element of the reals. Now, if I want to write that in interval notation, it's really easy. It includes the point, so bracket, -2, and it includes the other endpoint 3. And by chance, I didn't make that on purpose. I didn't even notice what I had done, but by chance, the range has the exact same values as the domain. That was fluke. Okay, won't normally be that. How does that differ from the next graph? Well, the next graph has this open point, not a closed point. So it's just a subtle difference. X such that -2 is less than. It doesn't include -2, but it includes 3. Just like that. Okay, our range. Well, our smallest y value is at -2, but it includes it. And our largest y value is 3, but we don't include it because it's that open point. Y is an element of the real. And we put that chalkboard R is what that's called. You don't have to put that second kind of vertical line that I put there. That's just because I'm old. Okay, you could just put a normal R. Like it could just look like this, and everyone's going to mark it right. I just put that other line there because I'm old. Okay, don't hold it against me. Interval notation doesn't include -2, but it includes 3. So I use a parenthesis and a bracket respectively. And the same thing for the range, just like that. Okay, so that's how we're going to write our notation when our graphs are sandwiched in between 2 points. Let's try just a couple more. We're almost there. Now, you may or may not have seen these graphs yet. They're starting to get into more complicated looking things, but the idea is the same. It doesn't matter if you've played around with these graphs or not. I should be able to give you essentially any graph, and you should be able to write the domain and the range. So this next one here is called a parabola. So does my graph stop going to the left? Well, no, because this graph keeps spreading out slowly to -infinity, and it doesn't stop going to the right because it keeps spreading out to positive infinity. So what I would say then is the set of numbers x such that x is an element of the reals. In my interval notation, I would say -infinity to infinity. My range, well, definitely my range, my graph stops going down right there when y is 2. It has a minimum. So I'm going to say the set of numbers y such that all of my y values are bigger than 2, including 2. So y is greater than or equal to 2. Y is an element of the reals. In my interval notation, I go from small to big. So my smallest y value is 2, square bracket because it includes it. It grows without bound to infinity, and parenthesis because, again, infinity is not a number I can put my finger on the number line. Okay, so there's another type of graph where we have a mixture of where the input can be anything and the output is restricted as to what we have. All right, the last one here, this is called a rational function. This is probably like a complicated one for us to do, but let's do it. Like I said, it doesn't matter if you've seen these graphs or not, you should still be able to write the domain and range for these. So the red lines are called asymptotes, and they're lines that our graph approaches but never, ever, ever touch. Okay, so they're called asymptotes. So I again ask myself, I'm like, what happens here? Can my graph ever stop going to the left? No, it goes forever. Does it ever stop going to the right? No, it goes forever. But I've got this asymptote right here, the vertical one, when x is -2. So what I'm going to say is x, the set of numbers, x such that x can't equal -2, but x is an element of the real. So what I'm saying is x can be anything but -2. And the same thing for the range. The set of numbers y such that y, well, y can be anything because this graph never stops going down to negative infinity, never stops going up to positive infinity, but it stops. We can't touch -1. So y can't equal -1. Y is an element of the reals. There it is. Now to write that in interval notation, I'm going to do this. I'm going to break it up into two parts. So I'm going to say my graph goes to negative infinity, but it stops just before -2. And then on the other side of the asymptote, it picks up again. On the other side of -2, it picks up. So there it is at -2, and it goes to positive infinity. Now there is a symbol that we put in between here that it's nice if you know it. I actually don't need you to know it, which is strange, but it's a capital U for union. Okay, if you just put a comma in between those, you would be fine too, but that's eventually how we'll write domain and range when we get to calculus. Same thing for our range here. So the graph never stops going down, but it stops or it approaches -1 and it never touches -1. And then on the other side of -1, and it grows without bound to infinity. And again, if you wanted to, you could put that U there, and that U means union, just like it does in real life. It's a couple of things joining together. Okay, friends, so that should take care of almost every type of domain and range that you should be seeing and working with. Um, you'll just see different types of graphs, but they should all fit these situations. I hope that helps. I'll see you another time.